So welcome back. In this video we are going to discuss about linear transformations. So a function or a map T is said to be a linear transformation from a vector space to another vector space if it satisfies these two conditions. Now the examples based on the definition would be to check whether the following map is a linear transformation or not. So consider the first example. It is a function from R2 to R2 such that Txy is 3x plus y and comma 2y. So first we will begin with considering two random elements u and v from the first vector space, which here is R2, and take a scalar element from the field R over which the spaces are defined. Then we will check both the conditions. So if both the conditions are satisfied, then the given map is said to be a linear transformation, else it is not a linear transformation. So these are some more examples based on the same concept, which I will be providing for sure. Consider this example, it is an important one. So here it is another function t from R2 to R2 such that t x1 x2 is x1 plus x2 and x1 into x2. So since here product is present of elements x1 into x2, this is clearly not linear, right? So we can just say that it's not a linear transformation just by looking at it. But to write it systematically, we can either compute both the conditions and show that these conditions are not satisfied, or we can use simply a counter example like the one that I have used here. The first element I have taken is 1, 2 and the second one is 0, 3. Their addition is, that is the transformation of their addition, that is the transformation of 1, 5 is 6, 5. But if we perform individual transformations, we get the final result as 6, 2, which is not the same as the one above, right? So it doesn't satisfy the first condition, hence it is not a linear transformation. Now moving further, this is another type of question that could be asked. It is to find a linear transformation which gives 3x of a given image. Like we can zoom the given image 3 times. So to find this, we will consider the standard basis elements. Since we are discussing about R2 right now, we will consider basis elements 1, 0 and 0, 1. So their transformations will be 3, 0 and 0, 2, 0, 3 respectively. So using these basis elements, we will show or represent a general element. So xy can be written as x into 1, 0 plus y into 0, 1. Since these span the entire R2, it is valid. Now we will perform transformation on both the sides. So transformation of x into this plus y into this. Since we know the first property, right, we can distribute it. So t of x into this plus t of y into this. So this is nothing but a scalar alpha into a vector. So we will take the scalar outside. So x into transformation of first element plus y into transformation of second element. We already have the transformation here, right? So we just put it in place of t10. Then by solving this, we get 3x, 3y. So it is the required linear transformation for zooming an image 3 times, right? Now the next topic is kernel of a linear transformation. So let v1 and v2 be two vector spaces which are defined over the same field K, and T is a map from v1 to v2. So it is a linear transformation, it is given here. Then its kernel is denoted as kernel T and it is given by this. So this is basically a set of elements from the first vector space whose image is 0 in the second vector space. Okay, so the examples or the questions related to these are obviously to find the kernel of the transformation, right? But first, these are some important points. If the kernel is a singleton set, that is, if it is the 0 vector itself, then the transformation is 1, 1. And if both the vector spaces are finite and have same dimension, plus if the given transformation is 1, 1, then it is also onto. This I will be discussing further in detail. But first, let's look at an example. So here a transformation is given from R3 to R3 such that this, so we have to check if it is a transformation, then we have to find its kernel, and we have to check if it is 1, 1 or onto. First, to check if it is a transformation, the similar way we did before, we will consider two random elements from the first vector space, which again is R3 here, and we will consider a scalar from the field R. Then we will check for the first condition and for the second condition. Since both the conditions are satisfied here, the given map is a linear transformation. Then for kernel, we will write the definition first. Then we will consider another random element from the first vector space such that the image of this element is 0 in the second vector space. So since we know T of u is 0, we can simply find the matrix representation of this system, then convert it into echelon form, find the solutions. So these solutions are basically the elements of the kernel. So this is the kernel. This is the kernel of the transformation. For a vector space to be 1, 1 or onto, for a transformation to be 1, 1 or onto, the kernel should be a singleton set, right? Singleton 0. But since it is not that in this case, the transformation is neither 1, 1 nor onto. So there are some more examples similar to the one above. Now next topic is matrix representation. So it is basically used to check if the transformation is 1, 1 or onto again. That is, if the determinant of the matrix representation is non-zero, that is, if the transformation has a full rank matrix, then it is said to be 1, 1. If the inverse of the representation exists, then the inverse obtained is the inverse map of the given transformation. Okay, I will discuss this deeply with the help of an example. So we need to find matrix representation of the following linear transformation with respect to the given basis. So here the linear transformation is from R2 to R2 such that T of x1, x2 is x1 plus x2 and x1 minus x2. This is clearly a linear transformation since there is no multiplication of the elements and all, right? The given bases are 1, 2, 2, 1 and 1, 1, 1, 0. So first we will consider b1 as u1, u2 and b2 as b1, b2. Then we will find the image of the first element u1, right? Then we need to find scalars from the field R such that the image of the first element of the first basis can be represented in the form of the elements of the second basis, right? That is, this can be satisfied, right? So to find this, we will obviously obtain the matrix representation, convert it into echelon form and find the solution, right? So this is the required equation. Then we will do similar for the second element from the first basis. Now the matrix representation will be this for the second equation. Here we have considered beta 1 and beta 2 instead of alpha for clarity. Then again we will do the echelon form transformation, and from it we will get solutions. Then the final matrix representation is obtained like this. Here this element is alpha 1, this is alpha 2, this is beta 1, and this is beta 2. So the scalars are to be placed in column, right? Column wise they are to be placed. So this is another example. Moving further, this is just finding matrix representation of the given transformation. So it is the similar steps, just the size of matrix is changing. Yeah. Now here we have to check if it is invertible. If yes, then we have to find its inverse. If it is 1, 1, it is onto, and we also have to find the kernel of the given transformation. So here again we will consider the basis as some vectors for simplicity. Then we will find their images, we will find some scalars so that we can show them with respect to the other bases. Similar steps, we will find the final matrix representation. Now this is the point which we didn't discuss earlier. So here we will find the determinant of the matrix representation that we just obtained. So if the determinant is non-zero, but here it is 0, so since it is 0, it is not invertible. But if it would have been a non-zero determinant, then that transformation is invertible, the matrix representation is invertible. Then we can find the inverse using the formula. We know that T inverse is 1 upon determinant of T into adjoint of the matrix T, right? We have been learning it since ages. So since it is not full rank, again it's easier to say that it's not 1, 1 or onto. We don't need to check other things. And kernel is the same. We need those elements from the first vector space whose images are 0 element in the second vector space. This is another one similar to the one above. Okay, so here this is kind of a shortcut, I'll say. So here this transformation is clearly from R3 to R2. So the bases are standard basis. So first one is the standard basis of R3 and second is the standard basis of R2. So the matrix representation here is literally just this. So 1, 1, 1, 0, 2, minus 1. It is the matrix representation that is needed. No need to compute anything else since the given bases are standard bases. So yeah, this question is the most important one. So here transformations or images of some elements are given and we need to find the general transformation. So for this we will consider the given elements as u1, u2 and u3. So they will obviously form a basis of the first vector space, which is R3. Choose any arbitrary element A. Okay, now we need to find the delta i's such that A can be represented using the basis 1. We find the matrix representation, convert it into echelon form, and then get the values of delta in terms of x. So this is the required transformation. So this seems different than this because I resubstituted the values of delta into this equation again, and solved it, and then got this final result. I have not included the entire steps, but that's how you are supposed to do. Now if it is asked to find transformation of any random element, we just need to put 10, 20, 30 in place of x1, x2, x3 and get the image. Okay, I think, yeah, so that's it for this video. In next video we will be covering another part of linear transformation. So thank you.